Hello and welcome to this second video about my console display implementation. Before to start, I would like to ask you to subscribe if not yet done and to hit the bell. If you like my work and you want to recognize it, this is very important for me. What's the difference between this implementation and the one I've shown in the previous video is that as you might see, I have implemented the 7-segment counter that you can see in the upper right corner. This is a full simulation of the MIDI Universal Console 7-segment counter, so it works exactly in the same way. It provides two modes. One is the one that you are seeing here, which is the hours, minutes, seconds, frame mode, and the other one is the bar beats mode with bar beats, subdivision and ticks. Let's see the way it works. Let's run Cubase. Cubase is starting up. There you go. As soon as Cubase is up, it goes immediately into the default mode, which is the bar beats subdivision ticks 1, and it goes in a position, of course, at the first bar beat and subdivision. Let's open a project. There you go. As you can see, it gets immediately into the position of the project, so at 6th bar, 4th beat, first subdivision and 56th tick. And as you can see here, it goes perfectly in sync with what is shown inside Cubase. If you run the project, there you go, the counter start running again in sync with Cubase. If we stop, you see it's 10 to 4:30 and it's 10 to 4:30 on the display. We can switch on the hour, minute, second mode. There you go, and then we can run it again, and there you go, stop, and we are at 22 seconds 24 frames in Cubase here, and the same into the display. The implementation was definitely more complicated than what I was expecting. Here the issue is the synchronization and the quantity of data that the DAW download to the MCU. Of course, I mean, lots of data means bigger buffer, but bigger buffer means also, and in general, more requirement for processing capacity on the CPU, which means problems of desynchronization between the console and the software. So in order to get the things working smoothly, I've been forced to apply two change. One, I've been redesigning an important part of my software, of my application, I will show in a moment, coming to a definitely more complex design. The second thing is that I've been forced to enable the caching. The SAMD 54 has the capacity to have 4 kilobytes of cache. This is the cache residing very close to the MCU, and so communicated with the MCU in a very fast way. You can cache data and instruction sets, and through this mechanism you can give priority to some part of your code in order to be processed in a more efficient way. Unfortunately, together with benefits, there are also cons, and in particular, again, I got problems, and I still have some problem in managing the ring buffer and the processing of the data which are not managed inside the caching. At the end, as I was saying, the result works quite fine, but some compromise has been necessary. So there you go. This is a schema representing the main part of the software as it is in this very moment. In particular, I've been forced to redesign the second part of the schema, this one, treating the data coming from the USB, so in input in USB, and then going to the user device managing strips and the display, which is this one. So what I've done here, I've created a ring buffer managing the bytes coming from the USB input. This actually was already there even before the implementation, the current implementation. Then I have a function which is formatting the data coming from the USB and which is consuming the ring buffer. This function works inside the main thread, so in sync, and is kind of cleaning up the data coming from the USB, because that data coming from the USB has an important overhead that needs to be eliminated. As soon as the data are formatted, these are sent to a dispatch function which is making decision. If it's data going to the channel, so pitch pen, aftertouch, control change, or not on or not off data, this goes straight to the user output of the channel. This is channel 1, and then there will be more when there will be all the other channels. In case it is sysex, so the text that you see displayed inside the display, or counter data, which again are control change, they goes into 2 additional ring buffer tailored to manage sysex and control change message, and then consumed in an asynchronous way by 2 counters which are reading the data here and here from the buffer and sends the data to the display user output in order to then be displayed onto the display. It would be very good if someone can make some comment or have some suggestion in order to simplify. I'm saying so because on one side I'm under the impression that the design is getting really complex, and on the other side I'm really understanding that I'm getting close to the computational limit of this MCU. The SAM E54, as I remind, works as 120 MHz, which in reality means 120 millions of iteration of cycles per second, which, you know, in theory, not in practice also, it's quite a lot. But on the other side, there's a lot of work for the CPU coming from my software, and even more probably than from my software coming from the framework, so the ASF4, which is an abstraction layer standing in the middle between my software and the MCU, and which is, in my opinion, consuming an important part of the processing capacity of the E54. So that's it. I think that in next step I will be trying to optimize this software, also recovering some issue that I have currently around the treatment of the sysex messages, because as I was saying before, due to the activation of the caching and of the prioritization of critical software, other part of the software like this one are now a little bit more in trouble. And then maybe I will also implement a datetime feature inside the display. That's all. Thanks a lot for your attention, and see you.